Today's topic is high frequency response of RC amplifier. हाई फ्रीक्वेंसी रिस्पॉन्स में जो आपके इंटरनल कैपेसिटेंस हैं, जो इंटरनल कैपेसिटेंस आपने मेजर की थी in the Miller effect, they have a significant role. What was that? CBE, that was the capacitor which is lying between the base and the emitter, and the capacitor which was lying between the base and the collector, and both were of few microfarads. This was the relation we derived for the Miller effect. This internal capacitance, which is lying inside the transistor, has a significant role when we consider the high frequency response. The high frequency response means as we are using the input signal, which is an AC type signal, so there are range of frequencies, low frequency range, mid frequency range, and high frequency range. So the capacitor as the amplifier which we are using, the common emitter amplifier, it is resistor and capacitor coupled amplifier. So the capacitor has a significant, the internal capacitors has a significant role in high frequency response. Although the bypass capacitor does not have that significant role, the one which was the capacitor collector bypass capacitor, and the other one was emitter bypass capacitor. Now, if we draw the equivalent circuit for the RC amplifier in order to study the high frequency response, first of all, as you know, that there is a transistor. This transistor is the emitter end. It is grounded. Now the frequency, the collector, which is responsible to supply the input to the second stage transistor, they are coupled to each other like that. The output of one stage transistor is coupled with the input or the base of the second stage transistor. It is like that, or you can say that. And above it, there lies a resistor R, and from that resistor, you can see that there is VCC supply, and this VCC supply is given to this transistor also. And after that, there is the input, which is like over here. Here we provide the input voltage. So the base current, first of all, the input signal is provided to the base. Now, if we draw the equivalent circuit of this high frequency response in order to calculate the high frequency response gain, it would be like that. It would be replaced with the internal resistance of this transistor, then the current source. After that current source, we will be supplying the resistor R. Here the resistor R will be lying there. And after that, there was two resistor, as you remember, R1 and R2, and their equivalent was RB. We consider that it was equal to RB. And earlier, we have studied that R1 and R2 are selected in such a way that their resistance are much, much greater as compared to the internal resistance of the second stage transistor. So the functionality of this resistance, combined effect of R1 and R2 resistance, which is used for the voltage division, becomes non-functional. Now let's draw the equivalent circuit. It will be cleared more from you by drawing that circuit. First of all, here we have the internal resistance of stage 1 transistor, which will be supplied with the input signal. So if it is a base, this point will be the emitter point. Now comes the current source. This is the current source. This point is known as the collector point. Now again we move on. Next one is the resistor R, which is lying above the capacitor. Here you can see that this is the capacitor. Here it's lying like this. After that, the second stage transistor internal capacitance, or you can say the impedance. Next one is the internal, the two resistors R1 and R2, their combination RB. And lastly, the internal resistance of stage 2 transistor. So this is the whole circuit diagram. From here you can see, as you know, we select this RB is a combination of R1 and R2, and RB is much greater than RI2. So if there is much more opposition, so why would the current would flow from this? The current has a second path, which is RI2. It will flow from this. So this resistance RB, which is large enough, it will become non-functional. So we can remove that. Now, here the current IB base will be supplied, and this is the current source of the first stage transistor. It is supplied to the second stage, and you can see that second stage here lies a resistor, the internal capacitance or the internal impedance of the second stage transistor, and the internal resistance of this transistor. RI2 is similar to HIE. Both are similar. This is for the first stage and this is for the second stage. Both of these are the internal transistor. Now we have to measure. What we have to measure? We have to measure the gain. The gain is equal to GM, that is transconductance, into the resistance. Resistance here, the resistance is R, the reactance of the internal capacitance, and this resistance RI2. So the combined effect of all the resistance, we will mention it over here by the impedance. Now, here you can see that this impedance has three resistance. Impedance is a combined effect of all the resistance and the reactances. So what we have R, which is parallel to reactance of the internal capacitance, this, and it is also parallel to this second resistance Ri. So first of all, what we will do, we will calculate that impedance. So to calculate that impedance, as they are in parallel combination, 1 over Ri2 plus 1 over R plus 1 over XCIE. So as you know that the reactance of any capacitor is equal to 1 over omega C. So we can replace that with omega CIE. From here, first of all, I'm taking LCM for these two, R plus RI2 plus 1 divided by omega CIE. Now it will form R plus RI2 divided by R plus RI2 plus omega CIE. Okay. Now, further simplifying that, I should remove this one. So I'm further writing the final term. After the simplification, it will become R plus RI2 plus omega CIE R RI2. Taking LCM again. Taking the LCM again, we get this term. So finally, what we get over here, the impedance will be equal to RI2 divided by R plus RI2 plus omega CIE RI2. So this is the impedance. Now, as we have calculated the impedance, now we will put that in this formula in order to measure the high frequency response gain. So simply we will be putting that. I have already written the gain formula. Negative sign, as you all know, we are using a common emitter as an amplifier. So the negative sign is due to the 180-degree phase shift, which is lying in all common emitter transistors and when they are used as amplifier. So the negative sign comes here. So here I have put the value of the impedance. Correct. Now I will be taking the R plus RI2, RI2 over by this ratio common. So gain will be equal to minus GM R RI2. Why I'm taking it common? Because as you know, this term, as we have already in previous lectures, we have seen that this term is equal to the mid frequency gain. 1 divided by 1 plus mega CIE R RI2 divided by R plus RI2. So here you can replace this with the mid frequency gain. What is this? This is the high frequency gain, and this whole term is equivalent to the mid frequency gain. This term, this word. So our relation will become gain at high frequency is equal to gain at mid frequency divided by 1 plus omega CIE RI RI2 divided by R plus RI2. R and RI2 are the two resistance. CIE is the internal capacitance of the transistor, which is a multiplication factor of all the reactances of the capacitor. One capacitor which is lying between the base and the emitter, the other capacitor which is lying between the base and the collector. So it is a combination of all these reactants which we have calculated in a previous lecture of Miller effect. Now this is the relation. We can take it in a resultant form by considering the square under root. We take the square of each term and then the under root in the resultant form. So this is the relation. Now, in order to measure the phase angle, this radical term will represent the angle, that is the tangent theta is equal to negative of omega CIE R RI2 divided by R plus RI2. From where this negative sign comes? As you know that in the frequency response curve, you have seen that this was the frequency response curve. Here, the slope of the gain was positive. Here, the slope of the gain was negative. So this negative sign is reflecting that the gain, slope of the gain is negative. So we will be writing here the negative sign to represent that. So you can measure the phase angle for the high frequency response. It would be minus omega CIE R RI2 divided by R plus RI2. So the total phase shift will be measured by 180. As you know that the mid frequency response has a phase shift of 180 degree. So for the 180 degree, this is the response of high frequency. Now what you have to do, you will subtract it with the 180 degree, then you will can determine that the angle for the high frequency response. This is the phase angle for high frequency by measuring, by putting the values of different frequency. How can you put that values? As you know, omega is equal to 2 pi f. You can replace that it with 2 pi f. Now putting different values of frequency, you can determine different values, each with the corresponding value of the phase angle. And by that you can determine the total phase angle change. So this was the frequency response of RC amplifier, or which is based on common emitter transistor. Here you can use, you can see that the gain as a ratio between this, and for normalized form we can have considered that you can replace it by 2 pi f also. And for the normalized form, we have already considered that whether it's a ratio between the high frequency gain and the low frequency gain with the mid frequency gain, it is normalized equal to 1. And this is always, which is determined to be, what we have determined today is 2 pi f CIE R RI2 divided by R plus RI2 whole square. It is normalized to be equal to 1. So the gain ratio which we have studied earlier, it was taken as a normalized value to be equal to 1. For that normalized value, if this ratio is equal to 1, so we can consider that this radical relation, that is 2 pi f CIE R RI2 divided by R plus Ri2 is equal to 1. If it is equal to 1, you can replace it over here. If you replace over here, you can see that this relation will become 1 over under root 2. And as we already know that when we take the limit frequency, either it is low cutoff frequency or high cutoff frequency, it was taken at the point here. There was the mid frequency gain, here was the gain, and this was the frequency. When the mid frequency gain becomes 1 over under root 2, that is 0.707 of the mid frequency gain. When it becomes 0.707, then we take the limiting values, that is the lower cutoff frequency and the higher cutoff. So it is similar that the higher cutoff frequency will be determined if this level of frequency here, the gain, the ratio will be equal to 1 over under root 2. So when it will be becoming the 1 over under root 2, when this radical relation becomes equivalent to 1. So from here you can see that this result holds by definition, that high limit or upper limit frequency expressions is given by this. So from here you can determine the upper limit or the high limit frequency. How can you determine? If we say that when this relation becomes 1, at that point frequency is equal to the upper limit frequency or high limit frequency f2. So what will be the value of f2? Replace f by f2. So f2, by rearranging that, r plus ri2 divided by 2 pi CIE r ri2. So this is the relation for the high limit frequency. This is the limiting value. At this value, the gain become 1 over under root 2 of the mid frequency gain. So by putting that relation in this, by putting the relation this, the f2 is equal to 2 pi CI r ri2 divided by r plus. So the relation will become, here you can replace the whole thing. One plus f over f2 square. So this is the relation now, and from that you can also determine the phase angle, which will be equal to minus f over f2, as the slope is in negative. So for high frequency is negative. So f over f2, here we can see that it states that when the rate of f and f2 goes on decreasing, when it will decrease when f2 goes on a higher, we see that when f2 goes on increasing, the ratio between f and f2 will goes on decreasing, as it is similar. For the low frequency response, that phase was equivalent to f1 over f. So in contrast to the high frequency response, the phase angle is the relation, the ratio is opposite to that. So this was the high frequency response gain and the phase angle. Now by putting the different values of frequency ratios. That is, it could be f over f2 could be 10, 100 or 1000. By putting that relation in this form, you can determine the different gain ratios. That is high frequency and low frequency gain, different ratios, you can determine it. And by determining it, you will be able to know that, first of all, if I put the relation in it, if we consider this is the ratio, high over mid, if we consider that f over f2 is equal to 10, so I'm going to put the relation for 10 ratio, then it will become 1 divided by 1 plus 10 square. And here you can see that f and f2, as f2 becomes increases, because it is a high frequency, it has to increase. So the f and f2 relation decreases more and more as the f2 relation increases. So if this factor is very small, so you can see that if the radical term consists of 1 over f2, so its square term will obviously be also small. So adding 1 does not make any significant difference. So it can be considered to be approximately equal to f over f2 whole square. So instead of 1 plus 10 square, you can write over here the 10 square. So the square under root is being cancelled over here. So the relation between 10 approximately equal to. This has been done just to simplify our relation, or the equation. So AV and the AV met for f over f2 ratio is equal to 10 is equivalent to 0.1. So you can determine similarly with another form also. And if you want to convert it into decibel, you would just put the relation, that is 20 log of 0.1, and from that you can determine the relation. It will be equal to minus 20 decibels. So this was all about the frequency response, its high frequency limit, its angle. Thank you.